motion is any motion that is equivalent to a single component of uniform circular motion. And in simple harmonic motion, velocity is greatest in the middle of the motion and acceleration is greatest at the edges of the motion. The period of an object in simple harmonic motion is written as the letter T, and it's equal to 2 pi over the angular velocity. And the frequency is written as the letter F, and it's just equal to 1 over the period. Okay, so these three graphs show the position, the velocity, and the acceleration of an object in simple harmonic motion. The position of an object in simple harmonic motion is given by x equals the amplitude times the cosine of omega times t. And the equations for velocity and acceleration can be found by deriving the position equation, and when you derive it, you would get velocity equals negative omega times the amplitude times the sine of omega times t, and acceleration would be equal to negative omega squared times the amplitude times cosine of omega t. And sometimes the object doesn't always start doesn't start at equilibrium, and if that's the case, then there would be a phase shift in here, which would be given by phi. This is an example of a mass on a spring. It's a mass of 50 kilograms, which is attached to a spring with a spring constant of 5 newtons per meter. It's at an initial position of 5 meters and an initial velocity of 5.5 meters per second. You can use this information to find each of the following things written here. So to find the angular frequency, you can use this equation, omega equals the square root of k over m. You just plug in the values, square root of 5 newtons per meter over 50 kilograms, and you get 0.316 radians per second. And to find the phase, you know that at time t equals 0, the position is at its initial position and velocity is also at its initial velocity. So you can use the initial position is equal to the amplitude times cosine of phi, and the velocity equals negative omega times amplitude times the sine of phi. When you combine the two, you get this equation, and you can solve for phi by doing that. And the final answer is phi equals negative 74 degrees, which is also equal to negative 1.29 radians. You can also use this information to find the amplitude by using the same equation, and it's at t equals 0, so you plug in 0 for t. And when you solve for the amplitude, you get 18.1 meters. You can use the energy equation we provided earlier. Energy equals 1/2 k times the amplitude squared. You just plug in the values, and you get 819 joules. To find position, you just use the same equation for finding position, which is equal to the amplitude times cosine omega t plus phi. So this would be the equation to find the position. To find velocity, use the equation that you got by deriving the position equation, which is this equation here. And finally, to find acceleration, you derive the velocity equation to get acceleration equals negative omega squared times the amplitude times cosine omega t plus b. And this is the equation you would get.
One example of simple harmonic motion is a mass on a spring. This type of spring produces a force given by Hooke's law, or F is equal to negative kx. In this equation, x is the displacement of the spring from equilibrium, and k is the constant that describes how stiff the spring is. A large K indicates a stiff spring and a small k indicates a soft spring. Finally, the negative sign indicates that the spring force is restoring, which means that the force always works to return the spring to equilibrium. You can also combine Hooke's law with Newton's second law to get A equals negative k over mx in order to find equations for angular velocity, period, and frequency for a mass on a spring. Angular velocity is equal to the square root of k over m. Okay, the period is equal to 2 pi square root of m over k, and the frequency is equal to 1 over 2 pi times square root of k over m. However, if the spring is vertical, the force equation becomes kx minus mg is equal to ma to account for gravity. Sometimes it is useful to use energy to solve a problem. The potential energy of a spring is U is equal to 1/2 kx squared, and the total energy is the potential energy plus the kinetic energy, or E equals k plus U equals 1/2 mg squared plus 1/2 kx squared equals 1/2 ka squared. Okay, so this is an example of a problem for simple harmonic motion when a mass is on a spring. So in equilibrium, mg is equal to kx, and by solving for k, we say k is equal to mg over x. And since the period of the oscillation is given by the t is equal to 2 pi times square root of m over k, we have 2 pi times square root of x over g, because k is equal to mg over x, and if we substitute that, that's what we get. And then we substitute the x and the g to make it 2 pi is equal to square root of 0.10 over 9.8 meters per second squared. And then the period is equal to 6.3 seconds. Ta-da!
Another simple harmonic system is the simple pendulum. It consists of a particle of mass m attached to a string with length L. If the mass is pulled aside by a small angle and released, the pendulum will swing back and forth in simple harmonic motion. The period of this motion is given by the equation period equals 2 pi over angular velocity, which ultimately equals 2 pi times the square root of length over the gravitational force. From this equation, we can find the angular velocity and frequency. Angular velocity equals the square root of gravitational force over the length, and frequency equals 1 over 2 pi times the gravitational force over the length. From this free body diagram, we can see that the only force which points along the tangential direction is negative mg sine theta. Therefore, the equation for the restoring force is negative mg sine theta. Here's an example of a simple pendulum problem. The problem reads, on the moon, the gravity force on the moon equals 1/6 of the gravity force on Earth. A pendulum has a period of 1 second on the moon. For part A, what is the spring constant required for a spring mass system with a mass of 1 kilogram to have the same period of oscillation on the moon as the pendulum does? Here we'll use two equations for angular velocity, which is square root the spring constant over mass equals 2 pi over the period. So after squaring both sides and multiplying m to the other side, you can see that the spring constant equals the mass times 2 pi over the period squared, and then you just plug in the numbers from the problem. So you plug in 1 kilogram, 2 times pi over 1 second squared, and then you'll end up with 39.5 newtons per meter. For part B, it asks, will frequency be different if the spring mass oscillates on Earth? And since angular frequency equals the square root of the spring constant over mass, and that's independent of gravity, so the frequency will stay the same. For part C, it asks, what is the length of the pendulum? Here you just use the equation angular velocity equals the square root of the gravity on the moon over length equals 2 pi over period. After squaring both sides, you get that the gravity on the moon over the length equals 2 pi t squared, and then after solving for L, you get that the length equals 0.0414 meters. The last part asks what would be the period on the Earth. Using the same equations as last time, angular velocity equals the square root of gravity over length equals 2 pi over period. You solve for t this time and using the Earth's gravitational force 9.81 as g instead of the moon. So you end up with period equals 2 pi times the square root of length over gravity, and after you plug in all of the numbers, using the length that you found in the last part, you get the period equals 0.408 seconds.